my topic is caloronic solutions in 2D+1 spin fermion model and the mechanism of high TC superconductivity. Well, actually, I would like to mention also people who are involved in this work in that or another way. I'm grateful to Jan Zanen and Sergei Brazovsky and Konstantin Yefetov for very important and nice discussions and advice, and also to my ex-PhD student Peter Karpov and Timur Galimzyanov, who are either my co-authors or just were helping when this work was running, and it is still running. So the plan is this, but maybe, and the plot in the corner is actually the plot of Professor Uemura, which I a little bit changed for my personal needs. So I'm going to speak about this part of the phase diagram with the T-star pseudo-gap regime and superconductivity, and the theory so far cannot reach the other half of the dome, superconducting dome, and we shall see how it happens. So, but first, I would like to tell about what are calorons, and then what picture at least we see when we introduce them, and then we'll consider what is the difference between T star and TC, and what happens in between, and actually how is it possible that we have also hidden order in this system, and then what could be the relation to neutron peak frequency of this picture when it is probed by experiments. So actually, a few words about instantons and calorons. There would be next slide with a picture, but I just want to say that instantons were invented by Polyakov, Korsos, and 't Hooft to explain QCD, and actually these are single time events in the Minkowski space. Further on, they were considered also in Euclidean space with imaginary time to explain tunneling of macroscopic systems. Now, calorons were introduced by Witten in 1977, which are actually instantons, but at finite temperature. And when the temperature is finite, the thickness of the Euclidean space with imaginary time is finite, because it's divided by one divided by temperature, and when temperature is not zero, so this is finite thickness. So calorons are actually periodic in Matsubara time and imaginary time instantons. And here are the pictures. So if this is the axis of imaginary time of the macroscopic many-body system, then instanton moves the system from one degenerate minimum of the free energy to another degenerate minimum of the free energy, and this single saddle point trajectory is called instanton. Now, calorons you can imagine as a periodic succession of these instantons when system moves from left to right and back and forth. And already from this naive picture, we can see that the instanton energy is lower, and for periodic motion, here the energy is higher, and it is related with the fact that this period between instanton and tie-instanton should be finite. So that defines how higher is the energy of this fluctuating order parameter with respect to stable one. So this picture of periodic instantons I have introduced long time ago, and at that time I did not know about the name caloron. So nevertheless, it is very simple toy model to explore them. And this is from Polyakov's book. We know that if we have such potential, that it is double well potential, and then we can find saddle point solution, which is tangent hyperbolic, and it is all in the book. But it is possible to find periodic solution of this system, just taking this equation again. And then it proves to be that this is Jacobi elliptic function, and the plot of this function in some not really precise way, but is here. So this function has very interesting feature that its frequency is also related with its amplitude. K is so-called Jacobi parameter, and it could be between 0 and 1. And when K is close to 0, so that the total amplitude goes to 0, the sinusoidal function becomes just usual sinusoidal function. And when K goes to 1, the sinusoidal function turns into tangent hyperbolic. So this is the general picture how it goes. Now, what is interesting here, that despite the temperature may go to 0, we may still maintain the oscillating solution rather than single event instantonic solution. And this is possible when we keep this product constant, because n is the number of instanton and anti-instanton pairs. And so we see when this number goes as 1 divided by temperature, so when temperature goes to 0, this number goes to infinity, and it means that the whole axis of imaginary time is filled with such a time crystal. And so this is not an occasional name. So actually Caloron is actually could be considered as a quantum time crystal, and the huge field of research now is in this area. But the first example of the quantum time crystal for such macroscopic system and with interferomagnetic fluctuations was given here. So next, what we are going to talk about. It is interesting to see what happens actually if this field, which we consider just abstract field, is not an abstract field, but a fluctuating spin density. And then we can compare how fermions would feel themselves in such a field. So imagine that we have some Hamiltonian where we shall see it later how it looks like, but where this periodic spin density influences fermions, and in the opposite case, when we would have a real spin density wave, system would sit only in one of its two minima. So it means the symmetry is broken and we have long-range order. In that case, we also may calculate the fermionic density of states. Well, in that case, we know it would be a gap. But what happens in the case when we have Matsubara time-dependent periodic motion? So it means that system never sits in one of its minima forever, but transitions from one to another. So it was proven in this paper that in that case, you can solve, you can find out the partition function in the way analogous to usual partition function with the mean field order. But here, the role of energy of the quasi-particle divided by temperature is played by so-called Floquet index. And this Floquet index is a solution for the Matsubara time-dependent Bloch equation, actually, or Schrödinger equation with imaginary time. And so it arises in such a way that we know that in periodic potential, we have Bloch wave. Here it's time periodic potential. So the shift of the wave function, when we shift potential by one period, is here, and this is Floquet index. But because this is imaginary time, here, this Floquet index is real. So it is possible to show that the partition function now looks like this. And you see very fine similarity between this expression and this expression. So let's see what is the consequence. The consequence is very funny. Namely, if we plot here the density of Floquet states of the system with Matsubara time oscillating spin density wave, and these are different type of oscillations. So nearly rectangular or weak spin density amplitude, which is nearly sinusoidal, then we see that the density of states resembles very much the pseudo gap situation. So this is Fermi level. And if we would have just usual spin density wave long range order with a gap, then the picture would be like this. So you see zero density of states in the gap, then peak, and then usual behavior. So we see that actually this periodic Matsubara time order parameter, which actually, as we shall see, is not long range order, but short range order, would induce this kind of spectral density of fermions, but in some sense, this spectral density is not so easy to see directly, because these are not the energies of electrons, but these are their Floquet indices. But there are relations between them. So after that observation, I would like also to mention our paper with Timur Galimzanov. We see that this picture which we found is actually consistent with the intuitive understanding that the caloronic state has higher free energy than long-range order mean field state. And in this paper, it was shown rigorously, but already from this picture, we can see why. Because look, here, the density of fermionic states is not pushed strictly from this pseudo-gap region. And this means that when we go to the left side of this axis, to the states which are filled, for example, by electrons, we see that electrons' energies are not shifted enough to the left, because there are pseudo states symmetric here, like they would be shifted in the case of a real long-range order. And so one might say, okay, this you can forget about these calorons, because the energy are always higher than spin density wave energy, and so no reason for them to occur. Because they are only fluctuations and high energy fluctuations. But then let's go to next slide. So here we consider a spin-fermion model, which was actually considered by many people, but I refer to Chubukov and co-authors review in Advances in Physics. So this is two-component model. These are fermionic part coupled to spin waves, and spin waves here are described by antiferromagnetic spin waves centered at antiferromagnetic wave vector. So this is the Fourier transform of the spin wave amplitude, and this is just the term which shows interaction between different spin waves. So it's just non-quadratic term. So then we have this Euclidean action, or just free energy of this spin part. And we see actually that this is the velocity of spin wave, that this spin wave energy has minimum when wave vector is close to to antiferromagnetic wave vector, and nothing else. So the question is, where is here the double well potential? Obviously, it is absent. So now let's come to the major invention of this work and of this talk. So the question is, why this single potential well Lagrangian density, or just energy density, may turn into this double well potential? What may cause this transition? And before we go to this, now assume for a moment that this transition has happened. Then look here, this is a spin density wave inside this potential well. So these are just usual harmonic oscillations of the spin that give you a spin density wave. And if we calculate the propagator of this spin density wave, you can check that its amplitude is proportional to this factor, meaning that it is actually small enough. When lambda characterizes this interaction between spin density waves and assumed to be small parameter. Now, if we look here, we shall see that the corresponding instantonic propagator for the system that travels between left and right potential well is actually huge, because here the spin density wave coupling parameter in the denominator. So in that sense, if this is our glue boson by which electrons make exchange, then it means that somehow the amplitude of this, I would call it soft mode, is very high with respect to usual amplitude of the spin density wave. And so in that sense, we obtain the reincarnation of the little dream for giant pairing boson amplitude, which he tried to apply to organic conductors, but it proved to be that instead of superconductors, they became insulators because of the Piles transition. But what is also important, that this amplitude is along the Matsubara, so imaginary time axis. It's not along the real space axis. So let's go to next. So now the question is how this transition may happen. And it proves to be a very funny result that this may happen if simultaneously there is a condensation of Cooper pairs in the region where this transition occurs. So what does it mean? It means that it is possible to show that if besides the spin fluctuations, spin density fluctuations with antiferromagnetic wave vector, we have also the Cooper pairing in the system. This coefficient in front of m squared may become negative. And the equation that we have to solve is actually this equation, where on the right we have famous Eliashberg theory diagrams, where this dashed line is actually the propagator of the Caloron, which we are now familiar with, and which plays the role of the glue boson. And here I had shown only one step of this Caloron, because as we already discussed, it is periodic in Matsubara time. So this huge propagator amplitude now is sitting inside here. Okay, this is fermionic Green's function, and this is anomalous Green's function, which depends on the density of Cooper pair condensate. So, okay, this picture was described in this paper, and now I'm going to more details. What is important, actually, it proves to be that this equation has solution which starts from mu this coefficient already non-zero. So it means that system jumps from here to here with mu finite, and therefore it proves to be a first order phase transition. So now, well, probably I'll skip these details. We can calculate this instanton as a Caloronic propagator, and it is our so-called averaging over zero mode of the system. So it doesn't matter. It simply tells you that when you consider this periodic structure, the energy of the system does not change if we choose another point of zero time. So if we change the time reference along this axis, the energy, free energy of the system doesn't change, and this is called zero mode. So we have to average over this zero mode, and then we get this Caloronic propagator, and then we have to solve the Eli-Ashberg equations with this Caloronic propagator shown here. And actually, the physics is simple. So spin fluctuations is electron-hole fluctuations. Cooper pairing is either hole-hole or electron-electron pairing. And actually, when we have exchange of particles between these two pairs, so instead of two hole electron-hole pairs, we have two electron-electron and two hole-hole. This is how these vortices arise that couple spin density wave fluctuation to the Cooper pair fluctuations. So it was possible to solve this system of equations, and I just showed that it is quite complicated. But what is interesting, that if we assume that I'm sorry, I just was too fast. If we assume that the major spin density wave couples the points in the Fermi surface region, and this is picture from Konstantin Nefedov's paper, but there are many of them. And if we assume that we have here, instead of hotspots, which people consider now, in that times I was considering the nesting points. For hotspots, all these equations should be recalculated, but in somewhat analogous but different way. So then it is possible to reduce the Eli-Ashberg equations for the self-energy of the anomalous Green's function. So the self-energy characterizes actually the density of Cooper pair condensate inside the caloron. So it proves to be that it's possible to introduce new unknown function, which we call here sigma, which is time-dependent, Matsubara time-dependent function related with the anomalous self-energy. And it proves to be that the equation for that the Eli-Ashberg equation for the self-energy turns into Schrödinger equation, where the role of coordinate is played by the imaginary Matsubara time. And this is very funny result. And then the role of potential for this, well, to say particle, which obeys this Schrödinger equation, is played by our already familiar to us propagator of the caloron. And it proves to be that this propagator has a sawtooth shape. Now, okay, it's a long story to make it short. It proves to be that non-zero Cooper pair condensate inside the caloron appears when we have bound state solution in this tooth-shaped potential. And the lowest energy bound state solution was found for this tooth-shaped potential numerically. And so we got this self-consistency equation. So because this caloron relies on the negative coefficient mu, as you remember, that makes double well potential, and the solution is this. So it means that if we have finite spin fermion coupling constant and density of bare fermionic states at the Fermi level at the nesting point, and if we have this spin wave related spin wave related parameter, so at the temperature which looks like this, we get transition to caloronic state. So from single well to double well potential for the spin density fluctuations. And this temperature, which we call T star, as function of the coupling constant, behaves like this. Now, next, we should see what happens to the free energy of this caloron with these Cooper pairs. It is funny, but what happens is the following. So here is the free energy of the caloron with the Cooper pairs. And we see that when temperature is high enough, this free energy is positive. So we have, so that we have below this T star, the calorons are still the fluctuations. But when temperature becomes low enough, we can see that this expression will change sign. Well, of course, provided that mu is not very strong function of temperature, this was calculated. And so when this would change sign, it means that calorons with the Cooper pairs inside start to condense. And we call this superconducting transition. And so for superconducting transition temperature, then we obtain this formula. So dependence of Tc on, again, on the coupling constant, which we found from this equation. So here is the picture. So you see this is Tc as function of the spin fermion coupling constant, and this is T star as a function of spin fermion coupling constant. Except, of course, T star here doesn't go to zero as an usual phase diagram, but nevertheless, you can recognize quite famous picture of normal strange metal and superconducting state. So this all arises from just these two formulas, which are results of solution of Eliarberg equations with a caloronic propagator. Now, where is the hidden order? Because I promised you that we have also hidden order. So the funny thing that caloron is hidden order, because if we calculate the cross section, we should not forget that caloron is a fluctuation of the spin density. So now, suppose we send the beam of neutrons to scatter against caloron, so the spin density fluctuation. We know the cross-section looks like this, where this is imaginary part of this retarded, so-called retarded propagator, which is related with the caloronic function, periodic function like that. And if we substitute here sphenoidal function and average over this so-called zero mode, so time, which means that the average over position of the zero of Matsubara time, we get very funny result. We find that this scattering, that this is two particle Green's function, is actually quadratic with respect to Matsubara frequency. So to show this, it is better to show here. So when we make analytic continuation of this Green's two particle Green's function with a caloron, we get only second order poles, and it is known from theory that second order poles have zero residues, and therefore the zero order residues means that the imaginary part standing here is standing in this formula here is strictly zero for second order residues. So we get this final result that the scattering cross-section of the caloron is zero. So it is invisible. And that's why I call it hidden order. And well, it is possible to show this other way here because this is second order pole, so it is quadratic in the frequency. So it means this function is actually even. And if you calculate the exchange of energy between caloron and external source, like new mesons or a neutron with a spin polarization. So you see that this is odd function multiplied by even function, so the integral is zero. Now, is it possible to measure calorons, and how this may happen? Well, it proves to be that yes, it's possible. For this purpose, we need to calculate the excitations, or I would call this phonons of this time crystal. So time crystal is periodic structure, and its vibrations would correspond to phonons in the usual lattice. But this is time lattice, and here we have vibrations. It proves to be that in the presence of the caloron, the excitations branches of caloron could be found from solution of this equation. And when we substitute here the Snoidel-Jacobi function, this equation finally fantastically becomes Lamé equation. So the solutions here again are well known. And here I show the branches of excitations of the caloron, and you see that there is a gap between lowest energy of the caloron and first excited state of caloron. And it proves to be that if we assume that the energy inelastic scattering of the neutron beam, for example, the frequency of neutron should be such to excite the caloron from here to here, you find out that the resonant frequency of neutron peak should be proportional to the amplitude of the caloron, because this is just the result of the Lamé equation, solution of Lamé equation. And then we recollect that the amplitude of the caloronic propagator is proportional to the T star temperature. So in that sense, we have something reminiscent with yesterday's talk by Professor Uemura, who said that the frequency of the neutron peak could be related with the temperature, either or with the TC, or in our case with the, sorry for that, with T star. So to summarize, here we had shown that actually the T star temperature could be understood as the temperature at which there is a first order into caloronic state, which is short range, periodic in Matsubara time oscillations of spin density with Cooper pair, or just preformed pair condensate inside this oscillating caloronic regions. But because calorons appear as the fluctuations here at temperatures higher than Tc, the local superconducting density phase is not correlated between different calorons. So we don't have really superconducting state, but we have regions of fluctuating superconducting condensate of the radius of the caloronic radius. Then when temperature goes down and we reach Tc, the calorons start to condense. So because the free energy of the caloron with the Cooper pair condensate becomes negative, and at that moment, probably the phase coherence between Cooper pair condensates in different calorons appears, and we get the bulk superconductivity. I don't know what happens here, because in this case, there are no caloronic solution above, and maybe this may explain this part of the dome. Well, otherwise, of course, this work is still going on, and I hope to have some new results because the paper is now in preparation with a solution for calorons, also space dependence, not only time dependence. And thank you for your attention.